Howdy! Chapter 3, the electric potential. It's hard to imagine what life would be like without batteries. Everyone is certainly familiar with this common, real device. But just what does it mean when it says some device is a 9-volt battery? In fact, it means that there is a difference in the electric potential function between the two terminals of the battery of 9 volts, or 9 joules per coulomb. The definition of the electric potential function is therefore certainly the beginning point for any understanding of how any electrical device works. It would be convenient if the definition were simple. Unfortunately, physics is not always convenient. The precise definition is, for a given electric field, the difference in the electric potential between the points R1 and R2 is defined to be V at R2 minus V at R1 is the negative of the line integral of E dot dr. Okay, you've all seen a device that looks like this in every cheap hole remover that's ever been made. What happens when I turn the switch on, this belt goes around, rubs against a piece of plastic, knocks off charges. The charges end up on this sphere. So we're going to end up with this sphere with a lot of extra charge on it. As we know, charges make electric fields. The integral of the electric field will give you the difference in the electric potential. Dramatic things can happen. One of them is the air between this ball and this ball will feel a strong electric field. That will ionize the air, in fact make what's called a plasma, and we will see lightning going from here to here. The closer I bring the ball, the larger the electric field. That's what ionizes the gas. A strange thing happens if we bring a neon bulb, which the gas inside will feel that electric field, and we'll see a rather exciting phenomenon. The electric field ionizes the gas inside the light bulb, and even though I have not connected any power supply to the light bulb, besides the lightning which we saw the light bulb going on. Another dramatic of this illustration is called Jacob's ladder. Inside the box we have a huge power supply which creates a large electric potential difference between these two swords, which were graciously loaned to us by the Corps of Cadets. Down at the bottom, the distance between these two conducting blades is small. Therefore, the electric field will be very large, and the gas, the air, will be ionized down at the bottom. Once that air heats up, heat rises, so the hot air containing the spark will rise up until the distance between the two conductors is so great that the electric field is no longer strong enough to ionize the gas. This is called Jacob's ladder. The definition means that we have to understand the abstract E before we can understand any real electrical circuit like that in the cell phone, which we could not live without. The easiest way to understand this definition is to change the abstract E into the more familiar quantity F by multiplying E by the test charge Q0. Then multiplying both sides by Q0 gives us Q0 times the electric potential. Difference is equal to the line integral of the force dot dr. Since Q0 E equals F, the right-hand side is just the work done on the test charge. This means the left side is just the difference in the electric potential energy function that goes with the force F. Now we might appreciate all the effort made in our mechanics course to understand the potential energy function. It is the basis of understanding electric potential, which plays a fundamental role in this course. We need to remind ourselves all about conservative and non-conservative forces, since the function U only exists for conservative forces. You might recall that a force is conservative if the work done by that force is zero for any closed path. This is probably the most difficult concept we faced in mechanics. You will have to be able to calculate the work done by various conservative forces on test charges in order to find the potential energy function for a force. All you need to do then is divide by Q0 to find the electric potential function. Some forces are easiest to treat in Cartesian coordinates, and some, such as the Coulomb force, are easier in polar coordinates. For this, you need the velocity in polar coordinates. For many problems, you will be faced with seemingly complicated integrals, and the trick to doing them is to define the best origin for the coordinate system. Finally, you might remind yourself that if a force is conservative, the components of the force are just the derivatives of the potential energy function with a minus sign. And dividing everything by Q0 gives us the components of the electric field. Summary. The voltage difference between 2 points, also called the difference in the electric potential between 2 points, is defined by the integral of the electric field between the 2 points, V at R2 minus V at R1, negative line integral of E dot dr. Just as potential energy functions only exist for conservative forces, electric potential functions only exist for conservative electric fields. If the integral relationship between V and E holds, then there is a differential relationship which also holds. The components of the electric field are the negative partial derivatives of the electric potential function. You should expect a quiz where you will need to find the electric potential for a charge distribution consisting of a few point charges and also one where there is a continuous distribution like a ring or a line of charge. Gig 'em.